time together, we talked about atoms, right? Get rid of this, thin lenses. And we talked about the structure of the atom, atomic structure, something like this. We talked about the Bohr model. We talked about the protons, the electrons, and the neutrons. And we discussed how it kind of makes up everything around us, right? We named the particles, right? We named the proton as the positively charged particle, right? So the elementary charge. This is kind of our shorthand. Don't forget charge, we're using the symbol Q when we study electricity, right? This was our +1. We said the electrons were -1, right? In reality, if you actually put this into the sort of SI units that we're familiar with in engineering, this is 1.6 times 10 to the -19th coulombs, right? This is the SI charge, 1.6 times 10 to the 19th coulombs, but negative, right? So equal, opposite charge from each other. And then there's also the neutron, right? Which I'm drawing here with just an empty circle that had no charge, no net charge by itself, right? No fundamental charge. And so this is also 0 coulombs. Thank you very much. I mentioned how much smaller the electron is than the proton. And we said something along the lines of, if this was the size of our little golf ball, this was the size of the nucleus, and I drew it to scale for real, and I held it right here on the desk. We said that the first electron band would probably be somewhere near the ocean at Coney, right? Super, super, super far away. So the atom is mostly empty space. Far away from the nucleus lie the electron clouds, and in addition, the electrons themselves, if you can put a size on them, if you could try to measure their mass, you'd find they're much, much smaller. I think the number we talked about in class was about 1/1840th the size of the proton is how big the electron is, right, in terms of its mass. So the actual numbers in mass kilograms, if you wanted to know them, I believe it's 1.67 times 10 to the -27th kilograms. I mean, 27 zeros, right, to the left. And then roughly the same. If you round it, I think we can round it to about the same. People say 1.66. Slightly different size for the neutron, but it's almost the same mass as the proton, right? And then I think it's 9.11 times 10 to the -31st, I believe. I can look it up just on my notes here. But yeah, 9.11 times 10 to the -31st kilograms. So again, you can see 10 to the -27, looking at order of magnitude, right? Just this is like 1 times 10 to the -27 for either of these guys. These are 9 times 10 to the -31, so almost 10 to the -30, right? Almost 10 to the -30. So the three of them between is thousands, right? 1,000-fold difference, and that's where we get this almost, 1/2000th, right? To be more precise, the size of the two of them in terms of mass. So as a little recap, atoms are electrically neutral, right? We said that you can't tell them apart. They're indistinguishable. You take one hydrogen atom. We'll talk about hydrogen today, and we'll actually get to see something cool, right? Hydrogen atom is just a proton orbited by a single electron. That's it. Anything that looks like this in nature, anything with a single proton in it, we call it hydrogen. That was just the name we gave to this, right? And it's because you can't tell apart anything else that has a single proton and a single electron, except by maybe its energy levels, right? So, hydrogen, we also talked about helium, right? 2 protons, 2 electrons. Okay? The atom is stable in this manner. Who remembers what we call it if we were to take away, say, hydrogen's electron? Ions, right? Atom, neutral, right? Ion, you change the number of electrons, whether by adding, subtracting to that structure, which we would normally call an atom, right? And when we get to chemistry, we'll talk a little bit more about, again, the rules. You can't just add, 19 electrons to the hydrogen atom and make something new. It just won't go, nature won't like it, and it will not really be stable in terms of the energetically favorable states, right? So ions are when you strip electrons away or give new electrons into what was a stable atom. Okay, So I keep using this word stable, and I'm being a little bit imprecise when I say the word stable, but we talked about this in mechanics, right? Instability. If I lay this marker here and I could somehow get it to balance just on the edge of the sink, it's not going to stay for long, right? It'll roll right over. So we talked about unstable equilibrium and stable equilibrium. And we just went over the exam. We had the guy in the chair, and he was sitting there like this, and he was sort of balanced backwards. And we said he was in an unstable equilibrium situation, right? The equilibrium refers to the net force being zero, right? No acceleration in that system. But it doesn't necessarily mean that if you poke it, that it won't sort of fall or change state, right? At the microscopic level, there is energetic stability associated with this structure staying intact. We talked very briefly about trying to model back in the day the electron orbiting the positive nucleus with the Bohr model of the atom, right? And the problems that sort of ensued because you imagine that there's some sort of centripetal force keeping it in this constant speed orbit. Eventually it should lose energy, it should spiral into the center, and that doesn't really happen. So there's some sort of stability associated with this, even though, as we talked about this week and last week, that the positives and negatives being opposites should attract, right? Nature has some defenses in here. We also spoke very briefly, even more briefly, probably a week ago before this, about the idea that putting the two positives together in the nucleus, right? That's the helium nucleus, right? Helium, not hydrogen. Putting those two things together requires a lot of energy in the first place, right? These two positives should repel tremendously from each other. And we said in ranking at sort of the per unit level, gravity was weaker than the electromagnetic forces, right? And the strong nuclear force, the strong force was even stronger than that. So of the four fundamental forces, and we'll look at briefly just in a moment, very, very briefly, something with the fourth one, which is the weak nuclear forces responsible for a type of radioactive decay. When you think about it this way, I think I mentioned to you what Velcro, we talked about what Velcro was, right? Little material. I don't think I have any on my backpack, but a couple of you might on your materials. Stick, right? You can stick something with Velcro like this to the board. And yeah, sure enough, it's electromagnetic in nature and it's static and it'll stay there and gravity won't be able to drop it down. And I said that sticking these two nuclei pieces together, a proton and another proton being nearby, even though there's that 1 over r squared law, which says if I bring it 10 times closer, the strength is 100 times bigger, right, of repulsion. If I bring it 100 times closer, then it's 10 to the 4th times as strong, the repulsion. You would think they'd repel, but the strong nuclear force is so strong that it keeps them bound together once they get there. If you put them fast and hard enough and you stick them together, it's like Velcro. You look at that force profile and you realize that it does nothing, nothing, nothing until you get really, really, really close. And when you get close, it spikes like this, real strong. You can't feel it, just like you can't feel the Velcro until you're right there. That was me throwing a tennis ball against the wall, right in the classroom. So this thing is stuck together, and it is stable that way, despite all of that energy, right? Despite all that energy trying to force it apart. Something else, another sort of balanced force, holds it in. When we speak about radioactivity, and now we're jumping ahead once again of lecture, and we're talking, we didn't even get to chemistry yet, but we're talking nuclear physics, right? Physics of the nucleus. Same name as inside a cell, right? Cell like a eukaryotic nucleus, right? When we're speaking about this, we're speaking about the stability of these structures, and sometimes they don't come out so well, right? Sometimes these structures don't hold together as well as they should. In the case of something called a carbon atom, okay, a carbon atom has 1, 2, 3, 4, 5, 6 protons. Anything in nature, arbitrarily, we give this a name because we can't tell them apart, right? And don't forget, of course, it's got 6 electrons, right? 1, 2, 1, 2, 1, 2. 6 electrons, we call this a carbon atom. I'm not going to introduce the nuclear notation and the charge and mass number notation right now. We'll do that in lecture. What I do want you to know is that a 6-proton atom, by definition, that element, we call it carbon. Literally an element, one piece of it, one piece of that substance, right? One atom. Now, in reality, I told you there's protons and potentially also neutrons. In the hydrogen atom, we don't have to worry about that, right? It's just a single proton by itself and then orbited by a single electron. But as you get heavier in the elements, and you have a periodic table right here, we'll teach you how to read it, what the patterns are, we'll teach you how to predict things without actually even knowing them, just by the logic and the math, okay? The carbon atom also has some neutrons inside it. So if I draw some neutrons, how many should I draw? 1, 2, 3, 4, 5, 6 seems like a reasonable number, right? And this is called, sure enough, a carbon-12 atom. Okay, a carbon-12 atom. 12 because there's 12 pieces in the nucleus. That comes to 6 positives and 6 neutrals, right? There are other forms of carbon in this world. There are other forms of carbon in this world, and those are forms of carbon that have an extra 2 neutrons. Okay? If you're looking at carbon with an extra 2 neutrons, that's called, not surprisingly, carbon-14. All right? It tells you the weight, the atomic weight of the nucleus, right? Why is it still carbon? Excuse me. Why is it still carbon? It's still got 6 protons, right? And that's it. Yeah, yes, Maria. Yeah, of course. That's what it is. That's the definition. It's still carbon by the fact, by the very nature that it has 6 protons. That's not changing, right? Not in this case, anyway. It's not changing. So it's still carbon. Is it an ion? Is it an ion of carbon? Carbon ion instead of a carbon atom? No. Why? The number of electrons are still the same. Still got 6 electrons, right? So it hasn't changed. Instead, this is called an isotope. Okay? Isotopes of an element are variations, different versions of that element that do appear in nature, or can be synthesized in some cases, right? That have a different number of neutrons in the nucleus, but the same number of protons as it's supposed to have for that element. Otherwise, it wouldn't be that element anymore, right? Carbon-14 is an unstable form of carbon in nature. Now, certain elements are literally so unstable that if you fabricate them in the lab, if you can sort of bring them to life within a fraction of a second, I mean 10 to the minus something seconds, they're going to be gone, out of existence. You can't see anymore, become something else. In a weird way, even though we think of the elements as something which is immutable, and that we can't transform, hydrogen into something else, or as the alchemists tried to do many years ago, like, aluminum into gold or something like that, right? There are sort of nuclear events that can happen that can disrupt the integrity and the structure of the nucleus, thereby turning you into new elements, or doing something to the electronic structure as well. So, in this case, carbon-14, this is your first example of something called radioactive decay. Radioactive decay. Radioactive and decay because something happens to disintegrate the structure of the nucleus, right? So carbon-14 becomes carbon-12. This is not standard notation. I'll teach that to you shortly, right? But something happens for nature to say, look, we really don't want these extra 2 neutrons in there. We'd rather be in our calm state, our happy place with the 12. This is not like those elements I mentioned a while ago where, they might be very short-lived in the lab, right? There's other things that, take longer than, half the life of the universe to decay, right? And you'll never observe it have a radioactive event. But carbon-12, we can sort of measure, and we have measured, how long it takes on average. Think of popcorn. You pop something in the microwave, you give it a little heat, and eventually the first kernel pops. When is that first event going to happen? It's random, right? It's a random process. But then the second event happens, and then the third event happens. And under the right conditions, they all start popping at different intervals, right? When the first one is going to pop over from a carbon-14 and become a carbon-12, we don't know. But we can get statistics on how long it's likely to happen between events, right? And this gives you half-lives and all the things that we'll talk about in lecture when we deal with nuclear physics. Carbon dating, if you heard of radiocarbon dating, right? This gives you a sense of how long-lived this thing will be before it comes back to become carbon-12. Okay, so how long-lived this carbon-14 will be before it falls down the slope and becomes a carbon-12. In this particular case, it won't actually make it. Okay? There are rules, as it turns out, the same way there are rules that govern whether or not we can slap, 19 extra electrons into a hydrogen configuration. There's also rules that govern what's sort of a legal move with nuclear reactions, okay? So in this case, it's not as though the carbon will just stay a carbon. When one thing breaks, several things break off with it. It's like when you break an object, right? This lid here is made of plastic and it's kind of got a chip taken off it, right? If I tried to pull one piece of gum off this thing, it might come with a chunk, there it goes, of this very old plastic. Do you see that? Right? So when this happens to the carbon atom, this carbon-12, and it wants to lose these two neutrons, it can't do it and stay a carbon. Like the alchemists always wanted, it turns that elements do sometimes change into one another, okay? And so the actual reaction here is from carbon-14 to nitrogen-14. Nitrogen is an element, another element on the periodic table. You can look it up actually right here. 6 is carbon, 7 is nitrogen. So a nitrogen atom would have 1, 2, 3, 4, 5, 6, 7 pluses, right? And then its own number of neutrons as well. As a matter of fact, you can tell me how many neutrons are in this. Because if the whole nucleus weighs 14 and I have 7 pluses, how many zeros, how many neutrals do I need to make 14? 7, okay? So again, I'm not gonna worry too much about the nuclear notation right now. I wanna teach you 3 examples. So I'm gonna grab my notes to see which ones I wanted to teach you, right? You have a carbon 14. I'm gonna use notation that's different from these notes. So you may not follow it exactly in the lab sheet, but this is how I like to write it, right? Carbon, 6 makes it a carbon. 14 is the variation of carbon we're dealing with. This thing becomes, it transmutes, it turns into nitrogen 714. Now, when we do nuclear reactions, we're gonna have to learn something very similar to those of you who have done chemistry. We do the law of conservation of mass. We did conservation of energy in lecture, we did conservation of momentum. There's also a conservation of charge, okay? And so without telling you the reason this happens, this is, again, the thing we'll go through when we actually do the theory behind it. What ends up on the other side of this equation is 1 electron. Just 1 electron, okay? This carbon-14, I wrote it upside down, I'm sorry, 714. This carbon-14 atom doesn't just magically become a carbon-12 because nature likes carbon-12. In this particular reaction that we're studying, it actually turns into a nitrogen and an electron. Okay, this is the example that's given in your lecture notes. So I wanted to stick with this one, right? This is known as the emission of something called a beta particle. Many years ago, they didn't know what electrons were, and they just found different types of radiation that they could detect. That was first discovered, and they said, we'll call this guy alpha, beta, gamma for ABC, right? Just giving it a standalone name. But a beta particle, we found out, the thing that they used to think was a beta particle is just an electron, okay? There are other kinds of radiation. Radiation being these chunks of energy or matter that are released from the reactions that happen at the nuclear level. Another type of instability inside a nucleus, I'm going to get rid of my carbon here for a minute. I'm going to get rid of the title nuclear physics because we know what we're doing, right? Another type is what you see in, sad day, right? But this is what we see with the nuclear fission. And we discussed this a little bit in class, right? So 92 protons is what makes uranium uranium. Okay, there's uranium-238, big, heavy element. Now you're talking, as the elements get bigger, the way they get heavier in the nucleus is not necessarily getting more protons, because you can't, right? Or else you'd be something else. The heavier elements, as you go down to the lower levels of this table, are getting heavier because there's more neutrons involved. So you can actually do that math in your head, right? 238 minus 92 gives you the number of neutrons that are inside that uranium, right? That version of uranium. When this guy decays, right, as in a fission experiment, he becomes something called thorium. Thorium has an atomic number of 90, and it weighs 234 atomic units. So you see we've lost some weight here, right? He went on a diet. He went on a diet, completely transformed who he was. And he went from 238 to 234, and the number of charge counts, or protons, went from 92 to 90. These numbers don't really make a ton of sense, right? Because we said that hydrogen was 1 plus with 1 minus, no neutrons, right? We said helium was 2 pluses and 2 minuses, right? Without any neutrons. How do you lose 2 positives and also all this other weight of 4 different units of neutron, right? Well, that's because I haven't been telling you the whole truth. You have in helium not just 2 protons, but you have 2 neutrons as well, right? So in the helium, the total weight, if you are being technical about helium, right? This type of helium here, it's positive charge of 2, but a total weight of 4. Right? This is the truth. This is how science goes. We tell you the truth deeper and deeper as you go along. This is what helium actually looks like. When this thing decays into thorium, another chunk comes flying off it that has to make up what the rest of it was. You literally see there were 92 protons and there were 238 neutrons. When this thing decays, it decays into a uranium, decays into a thorium, and something like this. It's a helium, but without the electrons. It's just a nucleus. It's just a helium nucleus. It's just a plus plus 0 0. All right, a helium nucleus. And this thing, years ago, they knew what this thing was. They knew that it could rip through other matter and cause a lot of damage, and that was called an alpha particle. Okay, they knew this thing was that. Now imagine what's actually happening here. Let me try to draw it for you a little more precisely, at least a visual. You have this big atom of uranium, right? A chunk comes flying off it in some nuclear event, and that chunk that comes flying off it is exactly the size of a helium nucleus, okay? So the electrons remain intact. This is the chunk that comes off, and this is the alpha particle, the helium nucleus, right? In this case, you're ejecting a single electron, right? So you have your carbon atom, there's your carbon, it becomes the nitrogen atom, and also, in addition to that, comes flying off, and we'll explain exactly in lecture why this happens, which makes this legal in terms of the rules and what things can't be legal, right? The electron comes flying off as well. You can imagine from mechanics that it literally comes flying off with a bunch of kinetic energy, right? Now, when I deal with fighters and athletes, okay, you can imagine that you have, you know, a boxer making a strike or something like that with a very small amount of mass. It could be very fast, right? I can hit the chair like that, and you see that jolt, right? You see that jolt to the chair, but there's not a lot of mass behind that punch, right? There's not a lot of mass behind that strike. If I put more of my body mass behind this, and even if I do it slowly and I move the chair, what happens to the chair? Okay? So you can imagine that this thing, regardless of the fact that they're both ejected at some sort of high velocity, if you want to use that visual, this thing being so heavy can rip through matter in a way that's a lot more dangerous, including your own tissues. So as nurses, you will learn about different radiation therapies, right? And the drawbacks and the advantages. So here, in this particular case, we have this heavy thing compared to this light thing, this electron, which weighs so little, 1/2000th of a single proton, where this weighs 4 times that of a proton, okay? Even though this thing gets ejected at high velocity, you can imagine a piece of paper, the electron goes through it and just punches a hole right through it, right? Whereas this thing, you can imagine, causes a rip and disintegration of the matter that it actually penetrates, right? All right, so this one is the most damaging of the 3 I'll discuss today, and this one's kind of like ranked in the middle. There's also something called a gamma particle. Gamma particle, and if you do the Greek letters, right, this is alpha, beta, gamma, right? A, B, C in our alphabet, right? In the Latin alphabet, this would be A. Same sounds are denoted by A, B, and C, right? We didn't know what they were back then. A A gamma particle is a little different. This is a particle of electromagnetic radiation. And again, because we're jumping from lecture, I will hold off on explaining this to you in exact detail. But we mentioned in lecture already that light that we see, as well as things like X-rays in the clinic, as well as things like the literal radio waves that you hear a radio station playing music from, and even microwaves when you microwave your food in a little microwave oven, right? These are all essentially just different colors, if you will, of light. Light is electromagnetic radiation. You can actually see that here. Gamma rays, X-rays, ultraviolet, infrared, microwave, radio wave, right? And you will have to memorize at some point in the class for your next exam the rough order of how strong these things are, right? How much energy they carry, and something about their wave-like properties, which we haven't gotten to learn yet. But the point is that you should know that this is electromagnetic radiation, not literally a piece of a nucleus that's coming off. This is some sort of energy being transmitted. Now, they say when you go to bed at night, you shouldn't have too much blue light, right? We kind of grew up as a species. You have the dawn and then you have the dusk, right? In the morning, you get this beautiful blue sky, and at night you sort of see like a little bit of a redshift, and they say that we were sort of adapted to that in the way that our melatonin cycles go in our brains, right? So blue light is particularly exciting to the brain because it's very high energy. Red, you'll see, tends to carry a lower type of energy, right? In the case of gamma rays, if you watch Marvel comics and you think about the Hulk or something like that, or you are an astrophysics buff and you're thinking about outside the radiation in the cosmos, gamma rays are a particularly high energy type of electromagnetic radiation. When we do chemistry, and even when we do Lab 6B, which is just in a few minutes, we'll talk about emission of light or other electromagnetic radiation that has to do with the electrons getting excited up and down, and that releases some sort of energy from the atom, and we'll tell you how that happens in a moment. But here, when you excite a nucleus, right, of an atom, you excite a nucleus, and this thing goes up in its energy, right? And then that thing falls back down. That, you can imagine, is a much, much bigger packet of energy than something like just shooting a color that we can see with that little device I was playing with earlier, right? And we'll get to see it in the demo as well. So when I say it releases energy, just think of something like this. Imagine I throw this marker in the air, right, and I don't catch it. I throw the marker in the air, I'll throw this object instead, right? You throw the thing in the air, you give it energy, you excite it first, and then when you hit the floor, bam, right? You get that sort of impact, and it has the ability now to send energy into the earth. That's the same thing that's happening here. You're gonna excite the nucleus, you're gonna vibrate it, you're gonna get it at a quantum level to absorb energy, and then when it falls back down naturally on its own, because again, unstable, doesn't want to be that tethered, right, on an unstable energy level, it comes back down, and that's what comes out is the gamma ray. The gamma ray, in some sense, is the most penetrating of all of these, right? If you have that large mass object here, it might rip the paper apart, but it won't go through several sheets of paper all at once. The alpha particle, sorry, the beta particle, right? The beta particle is in between. So this one is the most penetrating, right? Most penetrating. And this one is sort of the most damaging. In lecture, I will show you a YouTube short that I find really fun, and it's an old-fashioned joke that says, if you had 3 cookies and one contained an alpha particle, a beta particle, and a gamma particle each, which one would you hold out here, like I'm holding the marker? Which one would you feel comfortable putting in your pocket? And which one would you feel comfortable eating as a cookie, right? And the answer is more or less that because since the alpha is the most damaging, alpha is the most damaging here, you want to hold that thing as far as away you can, right, from your body, as far as possible. The beta is a little less damaging than the alpha particle, but it probably can be stopped by a couple layers of your own clothing, right? It's not as penetrating. So you can put that thing in your pocket and hopefully it won't go to your internal organs, cause DNA damage or anything like that, right? On the other hand, the gamma ray, it's so penetrating that no matter what you do, it's going to go through you anyway, so you might as well just eat the thing and enjoy it, okay? Fun little physics joke, right? Okay, when you think about what this does, these types of radiation, which by the way, all of these are called ionizing, right? Alpha, beta, gamma are all examples of ionizing radiation. And now we understand a little bit that radiation is something akin to energy or matter expulsion, right? We understand what it is. It's not something mystical. It's just pieces of nucleus or pieces of electromagnetic radiation or things like that traveling from one thing to another. Ionizing radiation, why? Because if it comes into contact with matter, one of the things it can do is it's so powerful and so high energy that it can strip the electrons off the matter, thereby turning atoms that it interacts with into ions. Ionizing radiation. When you do this in practice, okay, and allow ionizing radiation to pass through, say, like a gas or something like that, you strip the electrons off the atoms they're in, you create ions, and you release these little bursts of energy. These bursts of energy can actually be counted. We have sensors, and one of them is sitting right there, right? So the first demonstration, and I'm going to allow you guys to play with it after I demonstrate it. I'll demonstrate it, then we'll teach Lab 6B, and then you'll do both experiments on your own after I do the 2 demos. It's something called the Geiger counter. Again, named for a guy. There are a couple things named for gals in science as well, but this is an older scientist, right? An older guy who studied this, Mr. Geiger, right? Professor Geiger, I guess. And a Geiger counter literally counts separate events, multiple events of radiation ionization that's happening to matter, and it reports it back to you, right? So if it happens once, if it happens twice, 1,000 times, you bring this thing close to a radioactive source, and it'll go like that, right? It'll be like a stud finder in the wall. And you can hear the counts. Usually they have a click, audible. In ours, we have a number, right? You can actually read the number, and there's other digital ones that report directly to a computer as well. Although this is something that's not happening all the time to all types of matter, because as I said, there are rules, and certain types of things can break down. Some of it is just math, but some of it is just rules of nature, right? Certain things can break down in certain ways, other things won't break that way, right? Kind of like when you have a car and you design it, right? So the front bumper is flexible during an accident, and you don't want to crush someone inside. There's certain designed by nature that certain things can break off and cause alpha radiation, certain can cause beta, and certain can cause gamma. Although this doesn't happen with everything, there is a ton of events, right? There are a ton of events coming from outside in space to the Earth all the time. We've talked about radiation penetrating, right? The atmosphere, solar radiation is how we get our thermal energy, how we warm up, how life goes on, right? In addition, all the way back from when we talked about the Big Bang, in the very sort of nascence, the birth of the universe, there was a lot of this stuff happening, right? A lot of these high energy events. And so there is something called the cosmic background radiation. Nobel Prize was given cosmic background, I'll put BG radiation. That is all around us. There are small events like this happening all the time that you may not be able to observe with the naked eye. And that's why it's important, again, in the clinic too. You won't be able to feel the radiation damaging your tissues, but you have to be aware of it, right? We talked about the X-ray machine as well, right? Walking further away, the 1/r² law. But this stuff is happening in a low level, in a non-damaging way all the time. The Nobel Prize that was given was quite funny. They had this giant detector out in Bell Labs in New Jersey, and they had not been able to detect what they wanted to detect for months and months and months. And when they finally did, they wrote in their paper that they had to remove some sort of white dielectric material from the satellite, essentially, the sensor that they had outside in the contraption. And what they meant was that it was literally bird excrement that was just being collected over the years, and they had not been able to read the signal that they wanted to read just because that little bit of matter from the birds' bodies was causing it to barely penetrate and actually get into the sensor. So today what we're going to do is we're going to shove a couple of materials under the sensor. We're going to take a piece of plastic. We're going to take a piece of paper. We're going to take some aluminum and maybe even some lead, and we're going to see which ones block the signal the most. Okay, because we should, in theory, if this is everywhere in the whole universe all around us, in all directions, we should be able to pick up some of it anywhere we shove one of these sensors, right? That side of the lab, that side of the lab, up on top of a hill, all the way at Montauk, right? You should be able to detect this anywhere. So we'll try to detect it, and we'll see which materials block it. Which, if you had to guess, is the most defensive, the most protective material out of those three? Which one? The lead. Don't we have like one or two of you guys actually already working as a nurse, right? So the lead is also due to the dentist, right? When you sit at the dentist and you take the x-rays, they throw the lead over your body parts, right? It is so hard to penetrate the lead. And even when they use nuclear reactors, they have these arms, these control rods that absorb these high energy neutrons that are flying around and that's how we control the rate of the nuclear reaction, right? These sort of materials can help absorb these energetic particles, right? Any of these kinds. And if it was really neutron radiation, you wouldn't want to eat or hold or put that cookie in your pocket. That would be even further away. You'd want to be far, far away from that. It's much more damaging, right? Okay, so the Geiger counter, I will now try to demonstrate it for you. We can walk over here. We only have 2 of them and they're on this table. So I'll come to the back. Ashley, I'll come to yours if you don't mind, moving your notebook. And we'll just try to see what happens when we try to pick up any radiation that might be here around us right now, okay? And then we'll go back to the board and we'll talk a little bit more about the theory. So here we are. Here's our little tube. And I hope we can gather around to the best of our ability. What this thing is going to do is it's going to have a reset button on the right-hand side. I press the reset button, and it's going to count for 60 seconds, all right? Those of you that are on this side, for the benefit of those who are on this side, or just maybe for the video as well, shout out some of the numbers that you see. A show of hands, who thinks it's going to find basically 0 in 60 seconds, 0 radiation? Who thinks it's going to find, hundreds of counts of radiation in 60 seconds? Who says something in the middle? Something in the middle, okay? So let's try it, right? So hopefully this works. We tried it before. Reset, 60, 59, 58, 57, 56. It's counting as we speak. This is counting down the clock. You hear that click? Listen for it again. Nothing yet. So that was 4 I heard, right? 5. This is picking up the cosmic background radiation. It should be, yeah. I don't think I have anything in here that should be radioactive. So you got 30 seconds left to count, okay? But I've heard at least 10 clicks already, right? Beep, beep, beep. The old ones were literally click, click. It would sound like this. That's the old ones, right? All right, now we do New Year's. 10, 9, 8, 7, 6, 5, 4, 3. Keep hearing clicks, right? 33 counts. For those of you who can't see, right? 33 counts. And this is something which, if we do it again, and while we're discussing it, we can reset it again. If you notice, the first click took a while to happen. The second click took even longer to happen, but it was click, click, 2 and 3 right next to each other. It's a random process. On the chance that something crosses from the cosmos and hits us here at that exact sensor location, at that moment, it's a completely random event. But on average, there's a statistic to it, right? We can say what is likely, right? And we can say, not in the 1 minute, what is likely to hit us completely, but also what's the likely separation between one event to the next, right? That's the popcorn example, and you'll need to know that when it comes down to understanding what is like a half-life, which really for you guys is more important in, like, say, medicines, like, taking a Benadryl or something like that, than it is in radiation. But you'll calculate a whole bunch of them, and we'll do lots of practice about it in class. So here we have, again, 12 seconds, and now I'll count down 10, 9, 8, 7, 6, I'm still hearing your beeps, 5, 4, 3, 2, 1, and look at that, 33 again. So on average, right, we can run it a third time, and I'll keep going in class. We'll see if anyone sees a different number. Maybe actually you're sitting next to it. So this is the Geiger counter, and it's trying to pick up distinct events of when ionizing radiation flies through the cosmos, through the universe toward us, ends up smacking into the atoms in that sensor, and it sets it off, right? All right, what do we have to do next? When I release you to play with it yourself and try to give each other a turn, there's only 2 of them, so we'll have to split up into maybe groups of like 4, maybe max 6 people, and we'll go on it, take turns. You can try putting the different materials in it, and there's some space in your lab handouts, or you can do it in your own notebook to sort of count what happens if you place the shelf higher or lower, to block it. If you block it with the paper, you block it with the aluminum, with the lead, and so forth. Carl? This is 6A right now. All of the Geiger counter stuff is 6A. And we won't be able to do everything that's in the packet because we don't have all the materials, but that'll at least give you a sense and sort of a hands-on demo. Okay, it's 2 o'clock, so let's see if we can get on to 6B, and we'll talk about this now. So 6B now sort of gives us a transition. I'm going to erase some of this stuff, alpha, beta, gamma, okay? Don't forget, this is the high energy stuff, because you're going in and tampering with or dismantling the very core of what an atom is. You're tampering with the nucleus, right? And that's something that, again, there's rules, rough rules that we've learned as physicists to sort of figure out what are sort of the legal moves in that game, right? What are things that are really likely to happen and things which will never happen in 100 million years, right? What are things that can happen to a hydrogen is different from things that can happen to a uranium. So in reality, when you do chemistry or a lot of the rest of the sort of non-penetrative physics that we're talking about, there are things you can do to excite atoms or components of the atom that don't really get down to the nitty-gritty and start breaking the whole thing apart, right? And this is what I was saying earlier, is that chemistry, for the purposes of this class at least, is really just the consequences of the physics of the electron cloud and how these interact, right? So let's just take a look now for another example of what happens inside the atom when we excite the electrons. So the electronic structure, I'm going to give you a very, very rough cut. A very rough cut. We'll get into detail again as time goes on. We saw this Bohr model of the atom, which has the pluses in here and maybe the neutrals, right? And we had this electron going around it. That's a hydrogen atom from the Bohr perspective, right? So, in reality, I said to you something earlier, you may not have picked up on it. If this was the golf ball sized nucleus and the first electrons were, half a mile away or even a mile away over at Coney or something where the amusement park is, I said the first electrons. What did I mean by that? Well, helium has 2 electrons, even though hydrogen only has 1, right? And all these other atoms like carbon have got 6 electrons. Where do they go? So before I give the deeper picture, let's just imagine this simple one. Here's your plus, here's your nucleus, right? The first electrons, what I mean is that the orbit, we talked about centripetal force as the old idea, right, for how this is actually happening, keeping it in orbit. The orbit of the first set of electrons usually is 1 or a pair of them. There's literally just 1 or 2, okay? Is at a certain, you can imagine, a certain distance or radius from the nucleus. The next set of electrons orbits at a further distance, okay? So you have something like this. You have more electrons out here at a second distance. Okay, the next set of electrons orbits even farther, and I'm going to try to draw it as a visual, right? It's not exactly to scale, but they orbit even farther, okay? Now, I'm not being exactly technical, because in this first, what's called shell, this outer shell of the atom, right? The edge of the atom, if you will, you can hold, these 2 electrons, but in this one, you can hold like 8. Okay, you can hold more there. We'll get into the reasons why as time goes on, but you can hold 8. And then there's deeper pictures here as well that aren't just these sort of concentric rings, right? You can get deeper and say, okay, of the 8, where are the 8? Maybe 2 of them are going around this way, 2 of them are going around this way, 2 of them are going around this way. And I'm sure you've seen a lot of these pictures of atoms before, right? So that's 2, 4, 6, 8, that sort of thing, right? 2 of them here. And these 2, this can also be 8 when you're out here. But the point is that there is a general stratification or graduation of how far the electrons are said to be from where the nucleus is. So if the first ones are that far, you can imagine how far the farthest ones are, if you have an element that's big enough to have that many electrons. Now, the reason why they're far is they're simply at different energy levels. Let's try to put this into practice with our basic mechanics knowledge. When you have a centripetal force, right, your centripetal acceleration, here is Fc, right? You know that AC, the centripetal acceleration, is v squared over r. That's your acceleration, right? And you know that the force is just m times that, ma, right? So Fc is mv squared over r. But this v, this constant v that you have, going around that circle, round and round and round and round, is associated with the kinetic energy. Now that we know that, we can write that down. The kinetic energy is 1/2 mv squared, right? What happens if I wanted to have an electron at a higher energy? What would have to happen to the radius if I'm really keeping it at a constant speed around this atom, right? With the electric attraction keeping it there as a mechanism to provide the centripetal force, even in this silly model here, what would have to happen to the radius if I wanted that v to get bigger or the Ke to go up? If I wanted, think about the car, right? The car is coming around the curve this way. If I try to step on the gas while I'm going around a sharp curve, where am I going to go? If I try to accelerate farther, yeah, well, not completely straight necessarily. If I don't just fly off the circle, right? But as I try to go faster, it's going to push me out of the circle to get to a bigger circle, right? The only way to keep myself going faster is to widen my radius. Otherwise, my car would flip, right? I would not be able to maintain a tight radius at such a high speed. So to have more kinetic energy, I literally have to go around at a higher radius. You can use that as a way to visualize or remember how the electrons work. They have energy levels, and these energy levels, I made this too messy, so I'm going to redraw just this part here. Right, here's my nucleus, right? These are the pluses are inside here with my neutrals, and here's the first two electrons, right? These energy levels are labeled as such. N equals 1, N for number, okay? Just number. N equals 2, N equals 3. And you can see from the periodic table, once you learn how to read it, that the highest energy level that is available in that particular atom is given by the rho. So this thing only has an N equals 1 level because it's only got 2 electrons. So does helium, only has 2. So if 2 can fit in the first level, then of course it only has the first level. But once you get to lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, you can fit up to 8 more electrons. Each one has another, right? So they can have an N equals 2 level, right? And some of the electrons will be here. But once you go to the third level down, now you can fit more electrons because you have more protons, right? They have to balance. The protons and the minuses have to balance. So you can have a third energy level. So these big atoms like uranium, they can have lots of energy levels, right? Okay. Because light interacts with matter in different ways, we were saying earlier that the gamma ray is an example of something where the nucleus gets excited. In other words, its energy gets raised, but in an unstable way. It's in an unstable situation, and it falls back down, right? Just the same way as if you had kicked a ball up a giant cliff, a soccer ball. You kicked it, and landed here, right? What's going to happen if a tiny little bit of wind blows or a butterfly flaps his wings across the country, right? It's going to fall right back down. So this is the energy that goes in, and then it falls back down. As it does so, it releases energy, it hits the ground, right? Gives a little collision. Same sort of thing with the electrons. Now, hopefully we'll have a chance to understand at the quantum level, very, very slightly, how this physically happens or why this happens. But suffice it to say for today, that energy coming in typically from electromagnetic radiation, right? Causes an electron in one energy level to get excited so much that it moves up to the next energy level, okay? If you're ever wondering why they call it quantum physics, quantum doesn't just mean small, even though it's the study of small things. A quantum is a discrete, right? Quantum means discrete. Quantum, in Italian, quantistica, right? Quantum means a discrete something, not a continuous, right? Not continuous. Continuous. In other words, I can't just have an electron that has energy at level 1.3 or 1.759. It might have some sort of energy, but it's not going to be, it has to be discrete multiples, exact steps. It's almost like saying you can kick that soccer ball up a step like this, up another step like this, up another step like this, but there's no energy in between. Because if I try to kick that soccer ball, kick it like this, it lands here, boom, it hits the wall, it's going to end up here. It's not going to go in the middle anywhere, right? If I kick it hard enough, boom, all the way to the top, it's going to bounce here. You see that? That's what happens at the atomic level. You can put energy in, but the electron, the electron in the atom only accepts, these are the rules, right? Only accepts certain amounts of energy, these discrete packets of a finite exact size, no more and no less, okay? Those are the gaps, the exact energy differences between the energy levels. This is like saying I'm on a diet. I'm not just going to eat what I eat today. I'm going to eat only 100 calorie snack packs. And when I eat those 100 calorie snack packs, I know that my calories intake has gone up by multiples of 100. Make sense? If I eat 3 snack packs in a row because I'm starving, boom, I jump up by 300. But I can't jump up by 250. I can't jump up by 12. I can only jump up by multiples of 100 at a time. All right? So it is with electromagnetic radiation. If you've heard the word photon, this is another word for a particle of light. We'll explain what that is later. A photon, but you might see that in your packet or elsewhere. So you put a photon, a piece of electromagnetic radiation essentially, and you can excite one of these electrons and it can jump, right? So I'll erase some of these extraneous pieces of, so if I have an electron here in the first level, okay, it can jump up to the second level instead. It leaves here and it ends up here. it doesn't stay there for long, right? Even if I match it at its resonant frequency. It's like when you're pushing a child in a swing in the playground, you can't just push him at any moment, you have to time it exactly, right? If you get it exactly and Adam gets to jump with that amount of energy at that exact moment, it's still not gonna stay there very long, right? I mean, imagine I kicked my soccer ball up here, all the way, boom. It's gonna do this, it's gonna bounce, bounce, bounce. It's kinda gonna roll, and it wants to come back down. Make sense? It might fall down 1, it might fall down 2 or 3, depends on how high I put it and what the conditions are. But if you can actually absorb, if I write it like this vertically, enough energy to get you from n equals 1, let's say, I think the example I have in your thing is going to 4, right? So say you have 1, 2, 3, 4. See how I've spaced them unevenly? The same way that they're physically further away, and this makes sense, right? Because what we did with the 1/2 mv squared, right? The radius should get bigger and bigger and bigger, right? As the velocity gets bigger. This is 2, this is 3, this is 4. If I jump from, say, energy level 1 all the way to 4, I'm gonna fall back down. I'm probably gonna fall back down 4 levels, right? I can jump from 1 to 2 if I have the exact energy for this. 1, 2, jump twice to 3. And as I fall back down, what do you think happens to energy comes in, boom, now it's gone, right? Now it's absorbed by this electron, boom, it goes up. Now it falls down just like a ball falling down that staircase. What do you think happens when it falls back down? Another photon, or the energy, the electromagnetic energy is released. If you get it just right, and you have an electron give just the right amount of energy at just the right frequency so that it jumps to a specific energy level, right? The amount of energy that comes out is also characteristic of how far it falls down. If it falls from 4 to 3, if it falls from 4 to 1, the amount of energy that it gives off when it falls down is going to be very specific, right? It's unique to that type of atom, that element, and it's unique to the energy level pairs it goes from one to the other. The energy, I mentioned this earlier, but I didn't make it precise and quantitative. The energy of light depends on something called the wavelength. Again, we will talk about all of this when we study waves, but the point for us is that the energy is essentially proportional to the color. Red light doesn't carry the same kind of or degree of energy that yellow or blue light does. When we name the colors, say them with me please, the colors of the rainbow are red, orange, yellow, green, blue, indigo, and violet, right? In order of energy. So when you see the rainbow, don't we usually draw it red, orange, yellow, green? Make sense? Actually, usually the other way. We draw it back there. But you get the idea? They're in a band order of what type of color, or therefore what type of energy they're carrying. And if I told you that essentially gamma rays and X-rays and microwaves are almost like just different colors of light, now you can see that they're more energetic or less energetic. It's okay for radio waves to pass through us all the time, in our brains and our skulls. It's not so okay for gamma rays to do that, or even X-rays for that matter. And you'll probably calculate in your next couple of classes how much of a dose is okay, right? How many X-rays should you get in a lifetime? How many X-rays can you get in a week, right? My brother-in-law is a pilot. He's up there a lot closer to that background radiation than we are, right? 1 over R squared, so he's got to watch out in a different way than we do. All this to say, if a different amount of energy comes out when it falls between 2 specific energy levels, that means that different colors, literally, of light will be emitted, right? We might not be able to see this in our naked eyes in the everyday, but if you have a dark background and you heat up a gas to a certain degree, and then you excite it with the electricity, right? You're trying to heat up the energy of the situation. Another way to do this would be just to put something on fire, right? We did the magnesium lab last semester. We'll probably do it again with you. This bright white flash of light. Other things, sodium, I think a couple are listed in here. Potassium, lithium, strontium, barium. You light these things on fire. You ever see those fireplaces where they glow different colors? These are just different metals that when they get excited from the heat of the flame, they jump to specific energy levels. And when they fall down from those specific energy levels down to their ground state, they release specific colors. But a heated gas, that's an easier way for us in lab and a little safer. I don't really feel like lighting things on fire today, to show us that certain elements excited to a certain level from electrical energy, passing that current through it, right, will release specific amounts of energy off. and those will manifest as different colors. Now, mind you, not all elements release things that are visible to us. Some might release something in the infrared, the ultraviolet, or some other band of light that we can't see. But we have specifically picked elements for you that you can see today. So here we have hydrogen, all right? There is hydrogen gas inside this tube. And my good friend that I grew up with earlier today, who was not a scientist, was asking me all about hydrogen buses, right? So I said, this is funny because we're actually going to teach it in class today. This is hydrogen gas. When I run the current through it, I will excite it, and I will try to make it energetically at a higher level, right? These electrons, not the nucleus, the electrons, you might want to see this, you can see them physically falling down and releasing this energy back out to the world. Based on the color, you can tell how much energy is being released and therefore what level it got excited to. And that becomes important for designing any kind of medical apparatus eventually, right? It's going to take an instant, right? 3, 2, 1, go. All right, so here, I'll move around so you guys can come look at it. Do you see that characteristic pink glow? I mean, it is extremely vibrant, right? And it's a pure color. It's a single, what's called wavelength. Most colors that we see, we discussed this in class briefly, right? When light interacts with matter, pigments and filters, right? Most of what we see is a fusion of several things happening at once. This is not a pure color, even though it kind of looks like it. This is a bunch of different pigments in my shirt that are sort of conspiring together to show something to your eyes that your brain registers as like a teal or some sort of bright, maybe blue with a green tint, right? Let's see another color, right? So something like red. So Ashley's hat, right? This sort of like a purple or a fuchsia or something like that. Again, mixture of lots of different things. You have a similar colored hat. And Maria's got a red shirt on underneath, right? A bright red, but it's not a pure color. This is a pure color, a single wavelength. If there's ever such thing that a single color could be shown to you, it's when you heat a gas like this and you see a specific exact energy that's being transmitted. Now, neon signs are the same way, right? Neon signs are exactly the same way. You see these flashing neon signs on a highway, in Times Square, but neon, excited to a specific energy level, will give you a red color. It is a pure red, not like the shirt that Maria is wearing, right? It is a pure red, a single color, a single wavelength. So come around here and I will show you what neon excited looks like, right? So this is only one of the things you can do to neon. Neon can also be excited to other levels, right? Ready, set. It's almost too bright for me to stand next to, right? So this is a pure neon gas. This is neon, one of the elements. And as you ionize this by passing a charge through it, not something that's going to release beta or alpha particles, you're just exciting the electrons and they're coming right back down. Nothing harmful is really happening to us. It's releasing light that won't destroy us, right? It's a type of radiation that's a lot weaker than gamma, right? Beautiful. So this is neon, right? Now I left this to surprise myself. I don't know what the third element is because I didn't see. Let's see, we've got helium. Okay, so just above hydrogen in the periodic table, right? This one, let's see what it does. It doesn't do anything because it's not plugged in. But if I pass that energy in, right, if I actually excite it with the energy, ooh. So it looks whitish, but it's actually a pink. Can you pick it up? Right? So this is, again, a pure color. This is, I actually like it, yeah. It's not white, right? Yeah, I guess for me, if you see it against the, from my perspective this way, but now that I see the black against it. Now, when they did this in the 1800s, they did the same thing. They had to have a black background or a dark background where you could see the pure color. When they did this and they projected the light, you can actually see on that corner, I can point it out when I go back up there, the specific wavelengths of light that come out at specific energy gaps. They mapped them out, right? And when they did that, they figured out exactly what was the wavelength, what was the transition that was happening that they were observing. There's a fourth one, and it is right here. Joshua, sorry about that. This is nitrogen now. Is it plugged? It is not plugged in. Thank you, Jet. Let's do it again. Plug this guy in. Okay. Of course, yeah. 3, 2, up. Let's try this guy. It's broken. It's broken. That's because I plugged in the wrong electric outlet, wrong plug. It is not broken. Try it again. No, yay. All right. So nitrogen. That's the same thing as that one. Now I'm going to try to, it's similar, right? It's not exactly the same. I'm going to try to show you if I can bring that. Daisy, would you mind unplugging it? Thank you so much. You want this? Yes, please. Yeah. Thank you. I will try showing you the bottom, and I'll plug this guy in the top. Next to each other, this is nitrogen, and this is hydrogen, right? Not quite the same, right? Two different pinks. And then this one here, if you can see, I don't know if you can see this on the camera, but this is the other sort of pink, kind of a pale peach pink. This was helium. Yeah. This is helium, neon, but these are the ones that are close to each other, helium and hydrogen, these two. So now, I can't have you all do it at once, but if you'd like, if you take this viewfinder, what you can do is you can kneel down, and it has to be a certain way. If you go right up to the pink and you can find the pink in the little slit here, it will show you 3 colored bands on the right side. Those 3 colored bands are what you're seeing. The 3, actually in this case, it looks like it's 3 colors. Here, this is this one's like diffuse, yeah. And this one is, let's take a look at this one. This is like 4 or 5 colors. Those pure colors that I'm talking about, it's a mix of pure colors. So you can see, yeah, you can try them. Check them out. I'll give you a few minutes for everyone to do this afterwards, right? But I just want to see if I can point out to you up here, what's actually happening is, there you go. It's emitting light at specific wavelengths, right? It's exciting to specific levels, and those specific ones are coming down. This is how we make all kinds of things. All right, so if you guys direct your attention up here, where Ashley is, right, you can see here's a hydrogen spectrum. Spectrum, right, think of in clinical sense like an autism spectrum, right, is a continuous degree from one side to the other. This is not discrete, right? It could be any wavelength, any color, any between, right? But it picks some only. It picks discrete colors specifically. So hydrogen has a band here at 4100, 43 something, 40, this looks like 49, 48, 25 or something like that, right? Here's another one. Sorry, that was, it was hydrogen. Down here, 6500. This is like 65, like maybe 51 or something like that. In exact wavelength, which we'll learn what a wavelength is later. But the point is, an exact color of light. You put those 3 or 4 together, and that gives you exactly the pink that we see. Exactly the pink that we see. Here's our rainbow, right? This is the absorption spectrum. So this is like what you need to put in to get it excited. This is what actually comes out, right? This is the emission spectrum. Mercury, helium, look at this. Purples are in there, there's a pure blue in there, a pure yellow, a pure red, and a pure dark red. You put all that together and you get that kind of faint pink that we saw, right? I don't think we have neon on here, but you get the idea. You put these together, and these are the ones that you can get it to show. If it was only one specific wavelength, I'd see only one of these lights. But the electricity helps to excite multiple parts of it into multiple different emission events. Okay, and actually this is the tube we have right here. This is exactly what it is, and it's showing you how you can see it. So, awesome, thank you for watching. What I want you to do now is take a look at the board one more time, and I will try to just describe to you mathematically once, trying to leave the math without being too deep before we actually get into it in the classroom. The wavelength, more Greek letters. The wavelength, we use this letter, which if we had to give it a name, we call it lambda. Lambda in Greece. It makes the ul sound like an L in English. So the Roman letter would be this one, right? And this, although it has a specific meaning in wave physics, and we'll learn to measure it, it has to do with watching a wave and how long that wave goes. Specifically for us, this is going to tell us the color, right? The colors we can see are between something like 400 and 700 nanometers. So the longer ones, 700 nanometers roughly, that's like a red. The 400 nanometers, 10 to the minus 9 is nano, right? 10 to the minus 9. Those are, the short ones are like the blue, the purple, the indigo, the ultraviolet eventually, right? Butterflies and bees can see ultraviolet. In fact, they can see all kinds of patterns and markings on leaves. Like if this was a leaf, sometimes they can see like what looks almost like a landing strip, like this, an arrow that's a color painted in ultraviolet pigmentation on the leaf that we can't see, right? The wavelength and this sort of color in that sense of the light is proportional to something. It's proportional to the 1 over the n final squared minus 1 over n initial squared. Okay? It's proportional to this. In other words, it depends on how high is the electron going to go, how many energy levels is it going to jump, right? So where did you start, and then where did you end up? And specifically, there's a constant of proportionality, which is 91.15 nanometers. Again, this makes it equal. You can plug this in, and part of your homework for this lab is to go and submit to me if you could see n equals 5 to n equals 3. What should be the wavelength that you get? You can then look up, is it less than 400, meaning it's in the ultraviolet? Is it longer than 700, meaning that it's in the infrared, right? So you can calculate this. This is table section 3, the Rydberg equation. Again, two people, right? Balmer and Rydberg. These are two scientists who discovered this stuff back in the late 1800s, right? Okay, we're not doing the flame test. I guess the only other thing I wanted to tell you is that our very own sun, what kind of wavelengths do you think that puts out? All kinds, right? The sun puts out all kinds of wavelengths, all along this spectrum, right? All different ones at the same time, at the same moment, photons of all different energies. However, the ones our eyes are most sensitive. When I was a kid, I was learning that red, bright red, is a color that our eyes are very sensitive to. I've since learned that actually, see you soon, chartreuse, this sort of bright green that you see some traffic cones, especially in Europe, not always here, but actually a little bit probably yellower than this pen right here. I'm going to steal this from whoever is sitting here. Something a little bit brighter than this. That's actually the color that our eyes are most sensitive to. And the reason is because if you look at the emission spectrum of the sun, right, it's a little bit in this, it's a little bit in this area, and the place where it is the highest proportion of color it puts out is in that yellow, sort of almost green, but very yellow spectrum. So if you look out to the sun, please don't look at the sun. On many days, it's obscured by clouds, and it has this yellowish white look to it, right? Not like a bright white look to it. And that's just what dominates what's mostly being put out. And that means the sun is at a certain temperature, and it's putting out certain types of energy, right? So you can calculate this, and this is 91.15 nanometers, so 10 to the minus 9 meters. This is just level 1, 2, 3, 4, 5. This is just level 1, 2, 3, 4, 5. You do this, you find out the wavelength, and what you can do in your in your packet is to tell me then, once you find the wavelength, where does it lie on the spectrum? X-ray, ultraviolet, and so forth. I think that's everything we have for today. So what I'd like you to do now is I'd like you to go and take a look at the Geiger counter. I want the groups that are able to sort of pair up to sort of, oh, by the way, Ashley, what's the count right now? 32. 37. Okay, so we got 33, 33, and 37. So on average, we did 3 experiments. 33 plus 33 plus 37. We did it 3 times. 3 and 7 is 10, so this is like 40. This is 40 plus 30 is 70, 100. So it's a 103 divided by 3. So we have almost just a little bit more than 33, right? We have a little bit more than 33, 34, something like that, on average that we did in our 3 experiments today for how many counts we get, ionization events from the cosmic background radiation. So play with that. I want you guys to at least try before you leave. What time is it now? I want you to each try, each group, maybe each table can try putting the paper in the little slot, rerunning the Geiger counter. Putting an aluminum in the slot, which you can find in this container here. Yep. And these are, I believe they're all lead. I'm not sure, but I think they're all, these ones are all lead.
Which one is what? Like
it should have, I think it's all lead. I think the only one that's the aluminum is outside separately. So here you go. Piece of aluminum foil, right? And then there should be also a piece of paper that's here. So I want you guys, before you leave, to write down, if you don't have time to do all of the shelf levels, that's all right, but I at least want you to see what happens if you rerun the Geiger counter by itself, you run the Geiger counter with the paper, you run the Geiger counter with the aluminum, And the lead, yes. A stapler. You know, I used to. Yes, I do. And guys, I think that's it for the lecture. So please be good with each other. There's 2 of them, so you can do 2 groups at a time, okay? Thank you.